Welcome to the online Causal Inference seminar. Today we have Elizabeth Ogburn from Johns Hopkins, who will talk about social network dependence, unmeasured confounding, and the replication crisis. Very, very important topics. Her collaborator, Eugene Lee, is also with us today. She will answer questions in Q&A. But Elizabeth Ogburn will also stop from time to time to take questions from the audience. So please submit your questions to us. Afterward, we will have Ilya Shpitser from Johns Hopkins briefly discuss her work. And then if we have time left, we will also open the floor to the audience. All right, that's it from my side. I'm now switching over to Guillaume.
Right, thanks, Dominic. So as Dominic explained, Eugene, who is Betsy's collaborator, will be in the Q&A section answering your questions. So please submit them there. We'll select a few of them to ask to Betsy during her pauses. So if your question is selected, I will reach out to you via the chat and ask you if you're willing to ask the question live. And if you are, I will ask you to raise your hand. So you have a function on the menu bar to raise your hand. Please, please, please do not raise your hand until I've asked you to do so. Otherwise, it makes things more complicated on our end. All right, that's pretty much it. Betsy, the floor is yours whenever you're ready.
Great, thank you. Thanks, Guillaume and Dominique and all the organizers. This seminar has been a bright spot in my weeks under quarantine, and I'm excited to be on the other side of Zoom this week. Because this is the largest audience I'm likely to have in the foreseeable future, I'm going to take 1 minute to plug the coronavirus-related work that I've been spending all of my time on recently, only tangentially related to causal inference. But the COVID-19 collaboration platform is an attempt to give some order to the wild west of COVID-19 randomized clinical trials. Right now, there are hundreds of clinical trials being run across the globe, and most of them have no central organization, even though a lot of them are very small, underpowered, and most importantly, redundant. So clinical researchers across the world are all interested in the same set of questions about interventions for treating COVID-19. And we're hoping that this web platform will be a place for PIs of RCTs to share their protocols, to collaborate on existing protocols, and most importantly, to aggregate evidence across independent sites so that we can get answers much faster than if people continue to work in small, underpowered silos. So please tell all your clinical researchers friends to submit their protocols and collaborate. And we'll provide a lot of support for the collaboration and evidence aggregation. Okay, now for the talk. So okay, so today I'm going to talk about joint work with Eugene Lee, who was a student of mine and is now a postdoc at the Penn Center for Causal Inference. The talk is going to be about spurious associations due to dependence, in this case, dependence due to social network structure, and the relationship between spurious associations and some types of unmeasured confounding and the replication crisis in the social and health sciences. And I just want to caveat that the last third of the talk is my own editorializing about the paper that Eugene is first author on and that is to appear in JASA. So she is jointly responsible for the first 2/3 of the talk, but not for the last third. Oh. Okay, so I'm going to lay some background. So I'll talk about the inferential framework that I have in mind for social network data that underpins the rest of the talk. Then I will explain what I mean by spurious associations due to dependence, and I will try to convince you that this is a real phenomenon using a very pathological toy example, and then show you more realistic network simulations that illustrate this phenomenon. In my experience, a fraction of the audience, usually the economists, is very familiar with this idea, and it's kind of trivial and obvious, and the rest of the audience generally feels that this is totally counterintuitive and seemingly impossible. So I apologize if you're in that first camp, because I'm going to spend a bit of time trying to convince the other camp that spurious associations are a real phenomenon and that they're entirely distinct from causal confounding, although they can appear similar. Then I'll talk about a test that Eugen developed that can give us some circumstantial evidence for when spurious associations due to dependence might be an issue, and an application of this test to Framingham heart study data. And then I will come to the editorializing part of the talk, where I'll talk about the relationship between spurious associations due to dependence and certain types of unmeasured confounding, and nonparametric and parametric identification of causal effects in the presence of spurious associations. So this is a picture of a social network. This was created by Nicholas Christakis and collaborators using Framingham heart study data. I'll talk a bit more about the Framingham heart study a little later in the talk, but for now I just want to use this picture to fix some concepts. So the circles here represent nodes or people, and the lines represent various kinds of social ties that might join people together, or edges, network edges. And when I talk about social network data, what I have in mind is that we've observed a group of people connected by network ties like this, and each node has given us some data, maybe an outcome Y, an exposure X, some covariates C, and we're interested in doing inference about some functional of the data across the nodes in the network, usually averaged across those nodes. So we might be interested in the mean of Y, the mean outcome in the network. We might be interested in the association between X and Y, or the causal effect of X on Y. And there are many challenges for doing statistical and causal inference with this type of network data. But the one that I'm focused on is the fact that when people are interconnected like this, the network connections might induce some statistical dependence, in addition to all of the causal dependencies that I and others work on. I'm focused today on just the statistical dependence that can result when people are not operating in vacuums, but they're sharing all kinds of social and other connections with one another. So the underlying inferential framework for this talk, I won't come back to this explicitly, but this is really underlying the rest of the talk, is that when we observe random variables associated with the nodes in the network, and we want to do inference about those random variables, it's usually the case when you look under the hood in theory methods and application papers about this kind of data, that the goal is to generalize to other similar social networks. And the relevant inferential framework, therefore, is we want to know what happens under repeated draws of the same finite sample size n, from the joint distribution of the vector of outcomes, vector of exposures, and vector of covariates across the network nodes. I don't mean to be indicating that we're interested in finite sample inference in terms of the strategies that are used, but rather that even when we're using n going to infinity asymptotics, it's in the service of finite sample inference. So the relevant question is this dependent data sample large enough that I can use a central limit theorem for network dependent data to approximate what will happen if what I really care about is repeated finite draws of size n, or somewhere around there, from the underlying distribution. Okay, so what are spurious associations due to dependence? Well, when an exposure of interest, X, and an outcome of interest, Y, both exhibit dependence within X and within Y. So the X's are not IID, rather they have some kind of dependence. It could be spatial or temporal or genetic, or for the purposes of this talk, it's dependence due to social network ties. And similarly, the Y's are not IID. They exhibit dependence due to the same underlying structure as the X's. Then estimates of associations and of causal effects can be concentrated away from the truth. And this is the case even if the exposure and the outcome are causally and statistically independent from one another. So even under the null that there's no association and no causal effect, if there's dependence within the X's and dependence within the Y's, and the dependent structures are due to the same underlying space or topology, then tests of independence can tend to reject the null. And again, statistics can be concentrated away from the truth, the true null value. I just want to hammer home that this can happen in the absence of any causal confounding. So it's totally distinct from confounding. It can happen even if we're only interested in prediction. It doesn't have to be related to causal effect estimation. And it doesn't have anything to do with having a representative sample. So a comment that I get a lot when I talk about the challenges for using social network data is, well, obviously, if you're interested in a broad population and you're looking at an interconnected network, that's not going to be a representative sample. That is absolutely the case. That's an important problem, but it's orthogonal to the issues of statistical dependence that I'm focused on in this talk. So under the inferential framework that I discussed, we can specify, we can assume that our network is a representative draw from the joint distribution of X, Y, and C that we want to generalize to. So representativeness does not have to be an issue here. The issue of spurious associations due to dependence is a very well-known phenomenon in the econometrics literature on time series. It's known as spurious or volatile or sometimes nonsense correlations, and it dates back to Ewell. Similar ideas are hinted at elsewhere in the econometrics literature, and similar ideas are mentioned in at least 2 statistics textbooks that I've found. I'll argue later in the talk that this idea of spurious associations is related to what is known as confounding by batch effects and by population structure in GWAS and bioinformatics applications. But I'm not aware of any systematic treatment of this phenomenon outside of the time series econometrics literature, even though this can occur whenever data are dependent. It can be any kind of dependence, doesn't have to be limited to time series or genetics or social networks. But I want to caution, and I'll come back to this point, that any discussion of variance estimation is probably not about the phenomenon of spurious association. So it's well known that if you don't take dependence into account properly, you'll underestimate the variance of an estimator, and that's a real problem and one that I will mention later on in the talk. But that is a separate problem, and I'll come back to this later, from the problem of spurious associations. Okay, so here's a very pathological toy example to try to convince any skeptics that spurious associations are a real phenomenon and that they are totally orthogonal from confounding, totally separate. So let's say we have n observations. Each one gives us an X value, a predictor or exposure of interest, and a Y value. And I'm going to assume that the X's and Y's are causally and statistically independent from one another. But now I'm going to introduce some dependence within the X's and within the Y's that engenders these spurious associations. So let's say that the X's are a sequence that either trend upwards in subject ID or downwards in subject ID. And you flip an independent coin to determine whether it's upwards or downwards. And the same for Y. The Y's either trend upwards in subject ID or downwards in subject ID. And again, it's an independent flip of a coin that determines whether they go up or down. Now we observe a single collection, a single vector of n X's and a vector of n Y's. And now we want to estimate some measure of the association between X and Y. It could be a correlation, a regression coefficient, a causal effect. But no matter what which of these parameters we're interested in, we will always see in this single draw of n x's and n y's that the x's are either strongly positively associated if they're both trending in the same direction, or strongly negatively associated if they're both trending in opposite directions. And in a single draw, we will never see the true null value of 0. So in this particular pathological example, I hope it's pretty clear what's going wrong. The problem is that the target parameter here is a functional of the joint distribution of bold x and bold y, so the vector of n x's and the vector of n y's. And we only have a single draw from this joint distribution. Across multiple draws of n x's and n y's, we'll see that the association bounces back and forth from positive to negative and will average out to the true value of 0. But that true relationship between x and y is not identified from a single draw from this joint distribution, even as n goes to infinity. We just have no information in this one draw about the fact that x and y could have been either increasing or decreasing. We only see one realization of that coin flip that tells us whether they're increasing or decreasing. In more realistic, less pathological examples, it's not quite as clear-cut whether the association between x and y can be nonparametrically identified as n goes to infinity. And the examples behave in a slightly more complicated, less clear-cut way. Examples include, as I've said, time series, bioinformatics and GWAS examples, which I'll come back to at the end of the talk, spatial dependence, and then social network dependence, or network dependence, which is what Eugen and I focused on. So, and let me say that by network dependence, I really just mean the same kind of overarching type of dependence that people mean when they say temporal dependence or spatial dependence. It's dependence that is informed by the network topology, that tends to decay with network distance. It tends to be positive, but perhaps going to, or non-negative. It could go to 0, but it generally, at least in a systematic way, doesn't tend to be negative. So you can think of network dependence as any kind of dependence that decays with network distance. Okay, so here is what spurious associations can look like in more realistic settings. So this is a series of simulations that Eugen ran, where she first simulated a social network structure from a popular social network generating model. And then she seeded each node with an exposure x and an outcome y. In every case, x and y are independent from each other, but the x's have a variance covariance matrix that's informed by the network structure, and the y's have a slightly different variance covariance matrix that's also informed by the network structure. So there's dependence within the x's and within the y's, but x and y are independent from one another. And then she drew from the same distribution of x and y. I think these were based on 500 draws, and estimated the correlation between x and y in each draw. And this is a plot of those correlation coefficients. So in this first graph, actually x and y are IID. So there's no dependence within the x's and within the y's. And you can see that the correlation coefficient is tightly clustered in a tight bell curve around the true value of 0. And then as you introduce more dependence, we see that this bell curve starts to widen. And if you just saw these two examples with increasing levels of dependence, you might be inclined to think that this is the classic example of dependence reduces the effective sample size of a sample and therefore increases the variance. And you need to take that into account in variance estimation. That may be part of the story, but when you get to this case, you see the hallmark of spurious associations, which is that what's happening here is not just that the bell curve is widening because the effective sample size is getting smaller, but rather the bell curve is flattening out and then eventually concentrating around extreme values, concentrating away from the truth. So this is getting closer to the pathological toy example that I talked about. And no amount of variance correction is going to help here because the relevant confidence interval has to span the entire range of the correlation coefficient in order to cover the truth here. Okay, let me pause here to see if there are any questions before I continue on to testing for evidence of spurious associations in Framingham heart study data.
All right, so I have a couple of questions, some that are related to questions that were asked in the Q&A. So the first one is a very simple kind of clarifying questions. If the x's are randomized, so say you have a randomized experiment on a network, so the x's are randomized, but say the y's may be dependent. In this case, there is the spurious association that won't happen, right?
That is correct. Yes, this okay. It's a kind of story to explain why spurious associations happens. Is that if two people have similar x values, they're likely to be close in the network, and that means they're likely to have similar y values. So that's kind of the chain of information. So if one of them is IID, there's no problem.
Okay, that makes sense. And the second question is, and this is something that popped up in the Q&A, is, so you mentioned that this is distinct from unmeasured confounding. But can't we think of, so for instance, in the example that you gave with the x's increasing or decreasing with the index, and similarly for the y's, can't we think of the indices as being kind of like latent confounders? Or in the case of a network, can't we think of the kind of like the network capturing some or representing some form of latent state that's confounding x and y?
Yes, I'll come back to that in the end of the talk, but I'm glad you brought that up because I should have pointed out here that generally with unmeasured confounding, what you get is systematic bias. So this would not be the hallmark of typical causal confounding. You would tend to get concentration either in the positive or the negative area and not just the symmetric concentration away from the truth. So that is, in my mind, the kind of differentiating hallmark of spurious associations as opposed to confounding. But in the last third of the talk, I'm going to address exactly that question.
Okay, that makes sense. Thanks a lot. Let's see.
Okay, so the Framingham heart study is a hugely influential epidemiologic cohort study that was initiated in 1948, but is ongoing to this day. It was designed to study cardiovascular disease etiology, and thousands of papers have been published using Framingham heart study data. Hundreds continue to be published each year. And all of them, with the exception of papers that use the genetic SNP data that has come online in more recent years, all of the other papers, the papers that deal only with the phenotypes, use IID statistical methods to analyze these data. But when you dig into the cohorts, it becomes clear that they comprise a social network. In fact, it's the network that I showed you at the top of the talk. So the study population comprises 25% approximately of the entire population of Framingham, Massachusetts, which is a mid-sized town outside of Boston. Over 1,500 families have at least 3 members in the study population. And the study population, study participants know each other, they're neighbors, they're friends, they work with one another. So they're really deeply interconnected. And this makes Framingham heart study a perfect example of the type of convenience samples that's used throughout the health and medical and social sciences when researchers are interested in a population level study, but for reasons of convenience, they tap into a single community, a single hospital or medical clinic, a single school, or a small number of schools or communities or hospital clinics. So I think convenience samples comprised of one or a small number of social networks really run throughout the human sciences. And Eugen and I set out to answer the question of whether it's possible that studies based on convenience samples like Framingham heart study might be, first of all, reporting anti-conservative standard errors and confidence intervals and p-values because they're failing to take dependence into account in variance estimation, and this would inflate type 1 errors. And second of all, if estimates might be spurious due to network dependence. So to answer this question, Eugen adapted a popular test for spatial autocorrelation based on Moran's I statistic to test for network dependence. And she then found basically just the first 5 hits on Google Scholar for Framingham heart study papers from the cardiovascular epidemiology literature that were easy to replicate using publicly available data. And she replicated the analyses in these papers. They're all some form of regression. They're all interested in an association or a causal effect or a group of associations or causal effects, and they all use some kind of IID regression model to assess that. So Eugen replicated the analyses and then tested for dependence in 3 variables. So first, the regression residuals. And if we found evidence of dependence in the regression residuals, we took this as circumstantial evidence that variance estimation could be anti-conservative. Then she tested for dependence in the exposures of interest and the outcomes of interest. And if there was dependence in both the exposure of interest and the outcome of interest in a single model, we took this as, again, circumstantial evidence that there could be spurious associations, that the associations found could be spurious and due to this shared dependent structure rather than to a real association or causal effect. And we found evidence of dependence in all 5 of these papers. In 2 of them, we found extremely strong evidence of dependence in all of their analyses. And then in the other 3, we found a mixture of strong, moderate, weak, and no evidence of dependence. But in none of these 5 papers did we come away thinking we have found no reason to question the validity of the results reported on the basis of IID statistical models. And it was pretty surprising to us how easy it was to find evidence of dependence here. We also tested for dependence in a paper that I think we owe the current interest in causal inference in social networks to. This was a highly publicized paper by Christakis and Fowler purporting to find significant peer effects for obesity. So that's the causal, like a causal contagion effect of obesity through social ties. And again, we tested for network dependence in the outcome, the predictor, and the residuals from one of the regression models in this paper and found extremely strong evidence of dependence. So some caveats. We worry that a failure to account for network dependence in convenience samples could be contributing to replication crises in the health and social sciences, but this test only provides very circumstantial evidence. We can find evidence of dependence, but we don't have a way of linking that the strength of the test statistic to the probability of actual false positives. So we're working on making that link tighter. We can prove that these tests are valid. We can prove that they are powered for all of the alternatives that we care about, namely any kind of network dependence, any kind of dependence that decays with network distance. But this is a setting where conservative behavior means rejecting the null liberally. So to be conservative is to say, is to interpret a test statistic liberally as indicating we need to stop and not use our standard off-the-shelf IID models, but maybe try to do something more sophisticated to account for network dependence. So we would really like to understand the performance of this test in a detailed way under the alternative of network dependence, and that's something we're working on. And then the third caveat is that we were able to test for dependence in Framingham heart study data because Christakis and Fowler and colleagues went through the trouble of finding information about the underlying network structure. We don't need complete or fully accurate information about who's connected to whom in order to test for dependence, but we need some information there. And in most convenience samples used in the health and social sciences, we just have no information about who's connected to whom, so we wouldn't be able to run these tests. Okay, I'll pause again for questions, and then I'll get to the editorializing part of the talk.
All right, so we have a question from an attendee, but he hasn't replied to me, so I will just voice the question. This person asked whether this phenomenon also occurs if you have if you perform an individual level analysis of group data or clustered data. Maybe you have households or something like this.
Yeah, that's a great question, and the answer is no. If you have clustered data, you would expect spurious associations to flip back and forth across the truth in different clusters. So if you have a large enough number of clusters, the spurious associations will cancel out. Cluster data is essentially like having multiple draws from the joint distribution of the vectors x and y. If you have only a small number of clusters, this could still be a problem. If you have 2 or 3 clusters, then there's, with high probability, the spurious associations will not cancel each other out. But with truly clustered data and the number of clusters going to infinity, you're fine.
Thanks. That's very useful. I don't see any other question. Eugene is crushing it in the Q&A, so
great.
We're good.
Okay, so I started off the talk by trying to convince you that spurious associations have nothing to do with unmeasured confounding, and I hope you can see that this definition of confounding is totally orthogonal to the idea of there being dependence within the y's and within the x. So there's confounding by C if ignorability holds conditional on C but does not hold marginally. And this is, in fact, a totally distinct concept from spurious associations due to dependence. But C, the confounder C here, can be anything. And in particular, as Guillaume hinted in his question earlier, C can be a dependent structure. It can be a variance-covariance matrix, or an adjacency matrix for a social network, or some descriptor of the underlying dependent structure. And in fact, in a single draw from the joint distribution of the vector x and the vector y, there's nothing to distinguish between these two settings. In one setting, x and y are totally independent from one another, causally and statistically, but x has a dependent structure that's informed by the underlying network, and y also has a dependent structure informed by the underlying network. So this would be the spurious association setting. Versus, on the other hand, a setting where the underlying network structure causes x and causes y and is a true causal confounder. So let's go back to the toy example. And let's say that, so remember, x is either increasing or decreasing in subject ID, and y is either increasing or decreasing in subject ID. And C is a pair of coin flips, one telling us whether x is increasing or decreasing, and one telling us whether y is increasing or decreasing. And in the pathological example, I specified that the C's are independent from one another. But if we don't impose this restriction that it's independent coin flips determining the direction of x and y, then x and y can be causally and statistically dependent, and C is a confounder of the x-y relationship in the classical sense. And there is literally no information, as I pointed out up above, about whether the C's are independent or dependent from a single draw. If we only observe a single pair of Cx and Cy, we have no idea whether they're independent or dependent. And in fact, choosing to allow them to be independent, to force them to be independent or allow them to be dependent, indexes two different valid inferential frameworks. So if we imagine conditioning on C and just resampling x and y, that's a setting where Cx and Cy can be dependent. On the other hand, if we are assuming that in the true data generating process, Cx and Cy are independent, then doing inference under the assumption that they're independent corresponds to a framework where we're resampling C along with x and y. But both of these are valid because the distribution of C is a nuisance functional for what we care about, which is the association between x and y, and because the distribution of C places no restrictions on the observed data here, where the observed data is a single draw from the joint distribution of x and y. So we're really free to choose whether we want to treat x and y as independent, and that's the spurious association framework, or whether we want to treat them as dependent, and that's the causal confounding due to this dependent structure framework. And this freedom to choose goes beyond just this toy example. This is really true in general. And this brings me to some bold claims. So I claim that a lot of the literature that purports to be about unmeasured confounding is actually more helpfully viewed as being about shared dependent structure. So this is the case for confounding by cryptic relatedness and by population structure in GWAS. This is true for confounding by batch effects in computational biology and bioinformatics. And it's also true for confounding by cluster indicator or cluster level variables in any setting. And I claim that many methods that purport to deal with unmeasured confounding are actually tailored to deal with dependent structure that's shared between the exposures of interest and the outcome of interest. And they're not tailored to deal with causal confounding more generally. And this is why a lot of the success stories for methods to control for unmeasured confounding tend to be in computational biology and population genetics, because their confounding tends to be this shared dependent structure in the exposures of interest and the outcome of interest. In this case, it would be population structure or kinship structure. With the caveat that there are many exceptions to this. Lots of, so the biggest exception would be instrumental variable methods. It's certainly not the case that these are better designed to deal with shared dependent structure, and also the literature on graphical models with hidden variables. But for in large part, I think that methods that are designed to deal with unmeasured confounding, when you look under the hood, what they're actually doing is uncovering a common dependent structure that's common across exposures and outcomes of interest. And this is good news for us, because this suggests that if we are worried about identification of either associations or causal effects in the presence of spurious associations due to network dependence, that we can jump on board the many successful identification strategies that have been developed for unmeasured confounding in quotes specifically in GWAS and computational biology settings. A challenge here is that all of these methods require either knowing the dependent structure a priori or being able to learn it from the data. And it turns out that that's much easier in genetic and bioinformatics settings than it is in network settings, because we have a lot of, even if we don't know the full dependent structure a priori, we have a lot of knowledge about where that dependent structure is coming from. We know that it's coming from family trees or population structure or batch effects. And in social network settings, I think it's harder, but it's an open question. And I guess I will just mention here that methods for dealing with spurious correlations in the time series literature have a similar flavor in that they require either knowing or estimating the dependent structure and pre-whitening the data. So kind of removing the dependence and then dealing with IID increments, for example. But the same challenges apply to generalizing those to social network settings, that it's much harder to know or estimate the dependent structure in networks than it is in these other settings. But we gave it a try. So Eugen took some off-the-shelf methods that were developed for confounding due to cryptic relatedness in GWAS studies, and she applied them totally off the shelf to network data, both simulated and real. And as a proof of concept, we found that if you plug in the true variance covariance matrix for our network data, these methods perfectly recover true associations. So this is a test of the claim that we can use methods that have been developed for GWAS studies to deal with spurious associations in networks. That proves true. But these methods are not robust to misspecification of the variance covariance matrix. And even after controlling for the adjacency matrix, we found that actually only controlled for a minuscule amount of the dependence that we were able to detect in the Framingham heart study data. So testing for dependence and analyses that did and did not control for the adjacency matrix had similar amounts of dependence apparent. So this is all just to say that we need to get better at understanding the structure of dependence in social network data. And once we do, we have great off-the-shelf methods for controlling for spurious associations. Those strategies, though, are all parametric in one way or another. So either knowing the dependent structure a priori or estimating it from the data requires strong parametric assumptions. And what about non-parametric identification? Every causal inference person's preferred form of identification. So just very briefly, I don't have good answers for this yet, but I want to point out that in some cases, spurious positive and negative associations will cancel each other out as n goes to infinity. So this is the case for clustered data. It's also the case if x and y are jointly stationary. And you'll recall, let me just go back to these simulations. So there's a kind of middle area here when you introduce a moderate amount of dependence where it looks like as n goes to infinity, we might be able to do fine at estimating the association between x and y if we can account for the increased variance. But then you get here and you're in a case where clearly nonparametric identification is not possible even as n goes to infinity. So this is the case in the toy example that I gave above. It's the case for partial sums of two independent random walks. And in general, I think that we're left with needing to make another untestable assumption in order to get nonparametric identification. So I think assuming some kind of stationarity is likely to be an untestable assumption that's necessary for nonparametric identification of an association using a single, or a causal effect using a single draw from the joint distribution of x and y. I say partially untestable because there are tests for stationarity, but if you're interested, for example, in the causal effect of x on y, you have to assume that the causal structure is stationary. And this is a tactic that I've taken in my own work on observational data from a single causal inference for observational data on from a single social network. And I don't, at the moment, see a way around adding this new untestable assumption. Okay, let me just close with a brief discussion of some future work. So as I mentioned earlier, we can test for dependence in network data, but what we would really like to do is link evidence of social network dependence to the actual meat of the replication crisis, which is false positive associations and false effects in published papers. And we haven't yet been able to make that link concrete. In order to be able to control for the dependent structure that's giving rise to spurious associations, we need to be able to learn social network structure from the data. So that's an area that I and many other people are actively working on. And then I think formalizing the difference between cases where an association is and is not nonparametrically identified as n goes to infinity in the presence of dependence within x's and within y's is really crucial for specifying useful asymptotic frameworks for social network data. In particular, since I claim that we're using asymptotics that when we're dealing with social network data, we're using asymptotics in the service of finite sample inference. And this means that we really need to understand if the causal structure or the joint distribution of x and y is stationary across, let's say, large clusters in a network, what's the relationship between the scale of stationarity and the constants and rates of convergence for central limit theorems? We need to understand that relationship needs to be made very clear in order to answer questions like, is this n for my social network? I have a social network of size n. Is n large enough that I can use a dependent data central limit theorem to get approximate finite sample inference? And this is a wide open question, I think. And with that, I will thank collaborators. Eugen did so much of this work. We've gotten really helpful comments from members of various causal inference groups and many more. And then funding is from the Office of Naval Research Mathematical Data Science Program. Thank you very much.
Great. Thank you so much for your very nice talk. This network dependence is definitely a blind spot for many researchers, and we should pay more attention to it. We will now switch over to the discussion. Ilya will quickly present some slides. After that, Elizabeth can respond, and then if we have some time left, we will take some questions from the audience. So, yes, switching over to Ilya now.
Great. Thank you very much. I'm going to share a few slides I prepared. Can everyone see that?
Yes.
Okay, great. Okay. So I wanted to thank my colleague Betsy for a very timely talk. I'm going to talk a little, Betsy mentioned some COVID work she's doing, so I'm going to talk a little bit about COVID and just to give some context for Betsy's talk. You know, we're all going through this unprecedented public health crisis, and there is a real pressing need for informed public policy response. So we need principled analyses, basically. And so there's a lot of data coming out, more and more every day, but of course, much of this data is quite poor in various ways. And it's kind of interesting how this COVID crisis is just such a masterclass in the kinds of issues with data quality that sort of people in causal inference have been thinking about all this time. You know, we have all this data, but of course, for folks joining us from outside the United States, you may not be aware that we have a severe shortage of tests here in the United States, which means that the set of people who are tested is severely biased. There's a lot of censoring all over the place. There are false positives with tests of various kinds. And of course, there is dependence because people live in households and there are resource constraints in hospitals, and that induces dependence between experimental units. So there are all these recent studies coming out. So there was this recent one out of Stanford that sort of made claims that perhaps the seroprevalence, so the prevalence of COVID based on antibodies was much higher than we think. But of course, that study has been criticized because of the false positives of the test. And that's just part of the critique, right? So there are many other things you could criticize that study for. In particular, the way they did recruitment and various other things would induce all sorts of unit dependence, and people aren't even talking about that. And so I think this need that I think causal inference research underscores, which is that being clear and careful about all the assumptions you're making is as important as ever. And Betsy brings a very timely discussion of some threats to causal validity that we could encounter. And you know, the application area that Betsy discussed is not directly related to COVID, but of course, well, it wasn't in her talk, but it is directly related if you think about it for all these questions of prevalence and fatality and infectiousness. So the general idea, in the talk are that if we have unit dependence in general, we are in a sample size of one setting because we don't have a bunch of units. With the dependent structure, it's better to, so we're no longer IID, it's better to think of it as one large sample. And if you're in a sample size one setting, life becomes very difficult for you. So it's not just, it's a more fundamental issue than, you know, getting poor inference because you got the dependent structure wrong. It's more like our target of inference is not even identified. And I just wanted to just make clear this distinction in the kind of identification Betsy is talking about. So this is sort of finite sample non-identification. So we can't compute the variance from one sample. Which is distinct from the usual kind of non-identification causal inference folks worry about, which is distributional non-identification, which is something like, if I have an observed confounding and then I have a problem absent some sort of trick. So if I don't have an instrument and I don't have anything like a front door type structure, then even if I had infinitely many samples, if I knew the distribution of the observed data exactly, I wouldn't be able to compute my target. And so these are distinct. So they could both be a problem, but Betsy is worried about the first kind of non-identification. And some of the contributions that Betsy discussed was adapting a test for spatial autocorrelation to sort of network settings, and sort of using this test to provide some evidence that many published analyses that assumed IID data, in fact, have some network dependence in them, which of course is an enormous threat to their takeaway. And I just wanted to put all of that in context. In the causal inference literature, there are a couple of hundred people on this call who may not be sort of familiar with it. And bias due to network dependence is studied in the causal inference community under the keyword interference. And so the way classical causal inference works is we have treatment and an outcome, and treatment is not randomized, so we have some confounding. So we could have a drug and some like adverse health event and health status of a patient, because of course, if we're trying to save a patient's life, drugs are not assigned randomly, and we could make certain assumptions like absence of unobserved confounding or conditional ignorability, which I wrote over there as that independence, and lack of overlap or the present, sorry, like lack of non-positivity, so support for all treatment assignments. And informally, this kind of assumption says that you have a treatment that causes the outcome, and then you have this set of observed covariates that cause both the treatment and the outcome. And under these assumptions, you could evaluate average causal effects, which are counterfactual quantities in terms of this integral of two regressions called the G formula. And people have constructed lots of estimators for estimating this integral from data, which includes sort of plugin estimators and inverse probability estimators and semi-parametric estimators on the bottom, which have nice properties. And so that's the way the classical IID causal inference is played, where you have ID realizations from the observed law. And if we have network dependence, an easy way to generalize this game is to assume that we have IID samples from the same network on k units. So in the simplest case, on dyads, on two people, like a mother and child or roommates. And we then have to define our counterfactuals to define our causal effects on this network. So now you have inside the parentheses hypothetical treatment assignments to everyone in the network. And you could generalize network versions of the ignorability assumption or the lack of an observed confounding assumption to the setting, and then essentially proceed largely as before. So the paper I'm citing here is by Eric Chetgen, and Tyler Vandervelde in 2012, but there are many, many, many papers that do this. And unfortunately, there are many problems with this story. One problem is the network structure may not be known, which is probably the realistic example. If we're studying dyads, we could assume that dyads are dependent. But if we're studying a large network, like a set of rural villages in India or something like that, then probably we won't know the network structure exactly. So what can we do there? Well, we could, there are papers now that can derive some nice estimated properties anyways under some assumptions, even if we don't know exactly what the network structure is. Or we could adapt this causal discovery literature to try to learn the network prior to performing inference. And that's just assuming you have some data can be learned what the underlying causal structure is, or like causal graph or the causal network. So and another problem is we might not have multiple realizations of the same network. So this could happen if the networks, if the villages don't have the same structure, so it's not really the same realization then. Or it could be that the situation that Betsy was talking about in her talk, where you have one big sample of dependent units. Like you have one day snapshot data from Facebook or something like that. Well, in that case, it's very challenging. So this is the so-called full interference problem. And there's sort of starting to be some work on this. One of them is by Betsy and collaborators that exploited neighborhood independent structure. And another is by Eric Chetgen and friends who exploited kind of Markov field structure in the network to claw back some independence that was lost by assuming unit dependence. And there's lots more to do here. And there's quite a bit of recent work coming out. This is not meant as a representative list. And I just wanted to conclude by sort of reinforcing Betsy's point about the distinction between unobserved confounding and shared dependence. And I'll say the same thing in two ways, sort of the missing data view and the Yuda Pearl view. In missing data, the way we think about causal inference is we have the relationship between the observed law, where your samples come from, and the full law, which is larger, where your parameter lives. And we want to use observed samples to make inferences about the full law parameters. And so confounding is an assumption on the full law. For example, we could say that all counterfactuals are independent of the treatment assignment given a set of covariates. And this assumption, if we had samples on the full law, of course, we would be able to check, but we don't. We have a very coarse and smaller version of the full law called the observed law. And this assumption is not reflected in the observed law at all. It's invisible. It's an untestable assumption in that sense. Whereas shared dependent structure, in quotes, is generally something we can compute in the observed law. And perhaps a basic point here is that unless we intersect the full law with a very strong parametric model, never the twain shall meet. They're just different sorts of things. And of course, we can intersect the full law with a very strong parametric model. And Betsy discussed some examples of people doing that, where that's a sensible thing to do. But if we do that, it is important to be precise exactly what that strong parametric model is. In particular, it could be that we could check if the data supports assuming that model. And I don't know how many people do that. And Yuda Pearl has kind of a slogan version of the same story, where he says, confounding is a causal notion, shared dependence is a statistical notion, that we should keep causal and statistical notions separate on pain of serious problems with our analysis. And that's all I really had to say. So by and large, of course, I agree with everything that Betsy said. And I think it's a very timely talk. Thank you very much.
Thank you very much, Ilya. So I think we have time for maybe 1 or 2 questions. I have one person here on standby, so let me unmute him. All right, so Keleto, you should be unmuted now if you want to ask your question.
Hi, I'm Keleto. I'm a PhD candidate in social epidemiology at Harvard with an interest in social networks. I've noticed in the data that I've seen that real world social networks tend to have either many connected components, or if there is like one giant component that has variation in the density. And I wanted to ask whether that alleviates the problem of spurious association, and whether thinking about these disconnected components or connected components that are disconnected from each other helps with nonparametric identification of causal effects on the network.
Yes, so if you have components that are distinct, unconnected from one another, and you assume that that lack of connection means that they are independent from one another, then you're in a clustered data setting. And then as long as the number of clusters is moderately sized, you're fine, because the spurious associations will cancel each other out across clusters. I will note, because I saw that this came up a couple times in the questions, that is another hallmark of spurious associations as opposed to causal confounding. If you think you have causal confounding, having multiple independent clusters doesn't solve that problem. So it really only solves the problem of spurious associations that will be symmetrically distributed around the truth. In terms of a network that has varying density, it really depends on things like stationarity and the strength of the dependence between weakly connected clusters in the network. But I guess my intuition is similar to yours, that in many large real networks, nonparametric identification would not be a problem, that you would get regions of the network where spurious associations cancel each other out, and you'd be likely to have some level of moderate independence across portions of the network, and spurious associations that flip back and forth across those portions. But it's, technically speaking, it's very hard to link what you see about a network to this underlying untestable structure that has to be present in order to get nonparametric identification.
All right, thanks a lot, Betsy.
Fantastic, thanks. I think it's now time to wrap up. We're running out of time. Well, first, thank you so much to Betsy, to Ilya, and to Eugen today for volunteering to give a talk, to discuss, and to basically just coast through all the questions here in Q&A. Eugen did a fantastic job. Next week we will have Edward Kennedy from CMU, and as a discussant we will have Jamie Robbins. We are very excited about that. We hope to see many of you next week. And last but not least, we hope that you're all safe and healthy during these times. And thanks again for joining, and see you all next week.